Let's draw the transition diagram for this transition matrix. Now we can see that we've got two states. So what we're going to do is we're going to draw two circles, one for each state. Maybe this will be state A, this will be state B. And then we notice that, now remember how this goes. This goes like this, current to next. So this is current, this is next. So currently, if we're in A, the probability, now follow it down, the probability of going to A to A is 0.4. So when we write this, we're in A, we're going to go back to A, and that's a 0.4. And then if we're in A, currently in A, going to B, right, current to next, if we're in A, probability of going to B is 0.6. Now, these matrices, you know, are stochastic, meaning that all the individual elements in here are between 0 and 1, inclusive, and the columns add up to 1, right? 4 and 6 to 1, 5 and 5 to 1. So if we knew this was 0.4, this has got to be 0.6. And now, current to next, if we're in B, the probability of going to A, so if we're in B, the probability of going to A now is 0.5. So in B, going to A is 0.5. And then B to B, B back to B, well, if this is 0.5, this has to be 0.5. And sure enough, that's what's noted right here. If you're in B, probability of going to B is 0.5. And there's our transition diagram. And here in problem 2, this is the opposite of problem number 1. In problem number 1, we were given the transition matrix, and we created the transition diagram. Now we're going to go backwards. In 2, we're given the diagram, and now let's get the transition matrix. So you can see that we've got three states, A, B, and C. So let's write a matrix. Maybe we'll call it T is equal to, our transition matrix is, now, we have three states. I'm going to label them A, B, and C. And then, along the top, let's label these columns A, B, and C. And this will be our transition matrix. So we can see here that if we're currently in A, the probability of going back to A is 0.9. So in our matrix, remember how we go here? We go like this. We go this way. This is the current. This is the next. So if we are currently in A, right here, going back to A to A, that's 0.9. So this is going to be now let's get the same color here. So this is going to be 0.9. And then if we're in A, probability of going to B is 0.1. So if we're in A, going to B is 0.1. So if we're in A to B is 0.1. Now, these are stochastic, meaning that the columns add up to 1. So we've already got a 1 here. So this has to be a 0. And let's just check it. This means if we're in A, there's no chance of going to C. And sure enough, if we're in A, we cannot get to C in one transition, right? There's no way to get from A directly to C. So if we're in A, directly to C, probability is 0. And now let's look at B. What if we're in B? Probability, if we're in B, the probability of going to A is 0.2. So if we're in B, directly to A is 0.2. So we can write 0.2. And then if we're in B, the probability of transitioning back to B to B is 0.1. So B to B, that's a 0.1 right there. And then that only adds up to 3. So this down here has got to be a 0.7. Let's check it. B to C, 0.7. Run a check. If we're in B, probability of going directly to C in the next transition is 0.7. Sure enough. So this is 0.7. And now over in C, so what's the transition? What's the probability of going from C to A to B to C? Well, if we're in C, probability of going to A, let's look. If we're in C, there's no chance of getting to A in one transition. Now, we can get to A if we go to B and then to A, but we just want one transition. So C directly to A, can't do it. So that's got to be a 0. And then what about C to B? If we're in C, directly to B. So if we're in C, here we are, there's a 0.3 chance of going directly to B. So this is going to be a 0.3, and now this column has to add up to 1, so that's got to be a 0.7, but let's check it. If we're in C, the probability of going back to C in the next transition is exactly 0.7. So we've got it. Here's our transition matrix.